Welcome to Module 7. So let's get started. So Module 7 is basically the continuation of the hypothesis testing, but this time we'll be using sample data from two dependent samples, sometimes called the matched pairs, and conduct a hypothesis test of significance about two population means. And we'll use t-tests for this. And we'll also look at the testing the claim about two population standard deviations or variances using the newly introduced distribution called the F distribution. Before we get going, let's check on one thing. If you go to the Data tab, you should see a Data Analysis button up there. If you do not, here's how to add it. Go to File menu, Options, and Add-ins, and then just simply click on the Go button. This window should pop up. Make sure the Analysis 2-pack is checked and press OK. And once you go back to the Data tab, you should see the Data Analysis button. So once you get that, let's move on to dependent populations. So use this tab if the problem you're seeing in the quiz or the homework, it involves testing hypothesis involving the mean of the differences of the values from two dependent populations. So if it's about the mean of the differences from two dependent populations, this is the tab to use. And to do so, you need to be able to figure out some of those values. D, which is the individual difference. Mu of D is the mean value of the differences. And we set equal to 0 because the null hypothesis assumes that the mean difference between the two will be equal to 0. And the D bar is similar to the X bar, except that it's the mean value of the differences. So it's instead of X, we use D. And the S of D is standard deviation, and N is number of pairs, just like before, of the sample data. So let's do a quick practice on figuring out D, D bar, and then SD. So typically you'll be given the data such like this. So the first thing you want to do is figure out the differences. So simply just minus. That's what I did for all these. And then square each D's. So just square 2. So to do so, that's shift 6. That's called the caret. So B24 squaring that, and you get 361. So you do that all for all these differences. To calculate the D bar, it's this formula, or basically this is just the average or the mean. So you can either follow the formula or use the average function. There are 5 of them, 5 pairs, so 5. So S of D's is basically standard deviation of these D's, and square it to get 129.7. Follow this formula, and to get the standard deviation of D, just take the square root of that, and you get roughly 11.4 centimeters. Okay, so now you know how to figure out those numbers. Let's look at hypothesis test statistics. So as I mentioned, we'll be using T distribution, and there's a formula for the test statistic. And the confidence interval is written this way. So here's a formula. So let's look at an actual example. Using the data below and a significance level 0.05, test the claim that for the population of heights of a presidents and their main opponents, the differences have a mean greater than 0 centimeters, or we're saying that the presidents tend to be taller than their opponents. Is that the case? Let's take a look. So I reproduced the table just like above. And the null hypothesis that no, the mean difference is 0. There's no difference between the mean heights. And the alternative is that yes, there's a difference. The president seems to be taller than the main opponents. As I mentioned, the mu of D is 0, so that's 0. So D bar is just the average. So in this cell, I use the average function. N is 5. the variance here and the standard deviation just like before. Using the formula above, I calculate the test statistic here. And you can use a formula or you can use the data analysis tab, which I'll show it to you in a little bit. So either way you can do so. Degree of freedom is 4. And then since this is a right tail example, I'm going to be using the t.dist.rt function. If this is a left tail example, then you'll be using, say, t.dist, refer to the t, refer to the degree of freedom, and then comma true always. You do the similar thing if the problem was a right tail or two-tail problem. Okay. Look at the p-value. It is greater than 0.05. And also, we'll do this a little bit later on, but because the test statistic does not fall in the critical region, we come to the same conclusion. We failed to reject the null hypothesis. So the conclusion is there's not sufficient evidence to support the claim that for the population of heights of presidents and their main opponent, the differences have a mean greater than 0 centimeters. What we're trying to say is that the presidents do not appear to be taller than their opponents. So let's see how that works in the critical confidence interval method. So confidence level is set as 0.90. We figure out the t, and using that t, we come to the margin of error to be this number, following this formula. And the low end will be d bar minus e, so d bar from above minus e, this number, and then d bar from above plus e. And the interval will be somewhere between negative 7.7 centimeters and 14.1 centimeters. So what does that mean? Just like before, we have 90% confidence that the limits of negative 7.7 centimeters and 14.1 centimeters contain the true value, the difference in the height. So because the interval does contain the value of 0, it is very possible that the mean of the difference is equal to 0, indicating that there's no significant difference between the heights of the presidents and of the opponents. So we come up with the same conclusion as the p-value. So here, that's the rundown of how to do test hypothesis of two dependent populations and then differences in the means. So let's say you wanted to figure out t here, p-value here, and the critical value t down there using the data analysis tab. How do we do that? Well, first click on the data analysis and pick the last, or not the last one, but the t test, pair two samples for means. Click OK. And input the first variable range. So I select the first row, including the label. And for the second one, it's the row for the main opponents, including the label. If you do include the label, click on the labels checkbox here. This is the same as this mean difference is mu d, so we already said that's going to be 0. And alpha is 0.05 from the problem. And so I'm going to produce this in the new sheet. Press OK. Since I did that already, I'm going to go to the tab here. And that's what it looks like. Your output will not be color, but I just highlighted these in mind so that you can compare this to what you see in the lecture notes, so they're exact match. So that's the test statistic value, that's the p-value, and this is the critical value. And if you look at back at the previous tab, you see that they're replicated here, here, and here. So you can do either methods to figure out those values. I typically like to do it manually, so that's what I showed it to you here. So let's go to F-test. F-test involves two independent samples, so back to independent, with standard deviation 1 and standard deviation 2 unknown, and we're going to assume they're not equal to each other. So how do you compare standard deviations from independent samples? Here's how. Example. Subjects with the red background were asked to think of creative uses for brick, while other subjects were given the same task with the blue background. Creativity scored responses were scored by a panel of judges. Okay, so we're going to test the claim that those tested with the red background have creativity scores with the standard deviation equal to the standard deviation for those tested with the blue background. So we're saying that creativity variation is the same between two backgrounds, blue or red. So the alternative is no, they're not the same. So here's the data. We look at the 35 with the red background and 36 to blue background. X bars here and then standard deviations here. We're going to designate 0.97 as S1, the first standard deviation, because as a rule we set the higher of the two to be S1. So this is S1 and this would be S2. Doing the hypothesis here, we're saying the variance is the same or standard deviation is the same. And alternative hypothesis that no, they're not the same. So we're doing the variances because we're going to be using the F-test. So the value of F is calculated from this formula here, S1 squared divided by S2 squared. So that's what I did there. So now we know the first row is degrees of freedom 1, so 34 and then 35. Confidence level from 0.05 significance level, so it's not 0.95. So the critical value, there are two of them, left side and then the right side. Typically you're asked to figure out the right side, so to do so, use the f dot inverse function with this input here. And then if you're asked to figure out the left critical value, for example down here, you still use the f inverse, but you notice the difference that there's no 1 minus in the left side, whereas for the right side there's 1 minus. So if you're asked to find the critical values from the right side, do this. If it's the left side, do this. And p-values figure out by doubling the output from f.this.rt function. And this is basically the sum of two areas from here and then here. So that's the p-value using the f distribution. So since p-value is less than 0.05, there's sufficient evidence to warrant rejection of the claim that the two standard deviations are equal. What we're saying is the variation among the creativity scores for those with the red background appears to be different from the variation among creativity scores for those with the blue background. So we don't know how they're different, but we know they're different. So that's how you do F-tests. And that concludes Module 7.